So in this problem, we're asked how many Earth's radii would a geosynchronous orbit have to sit at in order to maintain itself. Now what that means is that at that distance, a satellite will rotate around Earth at the same speed that Earth rotates. So it'll have a period of 24 hours. So first, we're going to use the force, which is equal to minus g times the mass of the Earth times the mass of the satellite divided by the radius r squared, r hat, and that's going to be equal to minus g me over the radius of the Earth squared times the radius of the Earth over the actual radius squared m r hat. Now the reason I did this sort of manipulation of the symbols involved is that g me over re squared is just our familiar gravitational acceleration little g. And that's because that is the force of, or the acceleration due to gravity at a distance of 1 Earth's radius, which is exactly the surface of the Earth. So this gives us acceleration is equal to g times re over big R squared. I took out the m because I'm using only acceleration right now. And since it's in circular motion, we know that this also has to be equal to omega squared times r, which is equal to 4 pi squared r over t, the period, squared. Now manipulating this around, we can find that gt squared over 4 pi squared r, over 4 pi squared is equal to r cubed over the radius of the Earth squared. Now what we're really looking for is a proportion between r and the radius of the Earth. So we really want one more radius of the Earth turned out. So what we're going to do is we're just going to divide out one of those. So then we get r over re cubed is equal to g t squared over 4 pi squared re. And we can do that because we know what the value of the radius of the Earth squared, or what the radius of the Earth is. You can look it up on the internet. I believe it's in our textbook. And so that's a value that we can use. So plugging things in, we get 9.8 meters per second squared times t is going to be 24 hours, which in seconds is about 8.6 times 10 to the 4th squared, divided by 4 pi squared times the radius of the Earth is 6.4 times 10 to the 6th meters. And if you work all this out, you get about 287, and it's unitless because we have, this is seconds. We have meters on the bottom, and meters per second squared times second squared, so all of the dimensions cancel out. So now all we have to do is take the cube root. We get r over re equals 6.6, cube root of 287. So geosynchronous orbit sits at 6.6 Earth's radii away from the center of the Earth. So now for part B, we're asked that if 10,000 satellites are sitting in this geosynchronous orbit, which is one single band around the equator, if 10,000 satellites are sitting there, how closely packed are they going to be? So for that, all we need to do is we need to find the circumference is equal to 2 pi r, which is 2 pi times 6.6 Earth's radii. And then little d, the distance between them, between the satellites, is just going to be c over 10,000, since they're all sitting in that one line, is equal to 13.2 pi times 1 Earth's radii is 6.4 times 10 to the 6th meters, divided by 10,000 satellites, which comes out to be just about 27 kilometers. So if there are 10,000 satellites sitting in that one little band, each one is going to be 27 kilometers from its neighbor, assuming that they are evenly